So, hello everybody. My name is James Sunseri. I'm a rising fourth year at the University of California, Berkeley, and I'm presenting to you today my project on fast 4-point statistics for the turbulent interstellar medium. My project mentor was Professor Zack Slepian, and let's get started. So, the problem that I set out to answer with my project was how can we further probe for information about the turbulent interstellar medium efficiently? So right now, at the state of things, one can run like a 2-point correlation function, for example, which could teach you a bit about structure and like the layout or properties of a box. But there is valuable information that could be gained from going to higher order statistics, like, for example, the 4-point correlation function. So the only problem with that, though, is that these higher order statistics are typically really slow and infeasible to run on like a box of density or field. So my goal this summer has been to write a 4-point correlation function with order n log n complexity. And all that means is, or all that complexity means is just if you have n data points, then it's just saying that my algorithm would take n times log n calculations to complete and finish. So as this age of higher and higher resolution simulations and more data comes out that needs analysis on, it's crucial that we have faster and faster algorithms to, especially for the higher order statistics, to be able to look at these higher order phenomena and interesting things. And on the right here, I just wanted to show a nice little heuristic simulation of the interstellar medium, which I thought was really pretty. So in order to talk about my project, I need to discuss with you what a 4-point correlation function is first. And I've kind of spent a lot of time thinking about this. And I think the best way to say it is, so imagine you have a box filled with galaxies, and you have 4 points to explore all the structure of the galaxies within the box on a large scale. So how do you go about doing that? Well, first, what you should do is take 1 point of your 4 points and set that as your anchor point and put that on a galaxy. And now and it doesn't matter which one you start with, because you're going to look over all the different possibilities anyway. So we start with this anchor point, and then we have 3 extra points to look over the space with. Now, what we tend to do is we set these 3 different points at different galaxy locations, and we draw the distance between each of these galaxies and the anchor point as R1, R2, and R3. Now, what this shape creates is sort of a tetrahedron-like shape, and normally a really slow algorithm would look over all the different possible tetrahedrons you can create by capturing the geometry and discussing it in terms of just the side lengths or the edges. But that's really slow, and that would create like an n to the 4th type algorithm that scales very slowly. And we need to speed that up, because that's infeasible when you have even 1 million data points. That's going to be like trillions and trillions of calculations. So the way we speed this up to, like, say, an n² algorithm is actually removing some degrees of freedom. And the way we do that is kind of interesting. I say what we do is we look at the angular information. So it's kind of a similar idea to capturing the information of a triangle with side angle side as opposed to side side side. But the reason why we do this and why this is important is because we can actually expand these angles in terms of an orthonormal basis. And essentially that's like doing a glorified Taylor expansion, where you can kind of truncate at a specific order and cut the computation time down drastically. So essentially the way we capture all the information of the 4-point correlation function is by doing a sum over a bunch of radial coefficients projected onto an isotropic basis, and summing all that up gives us the full 4-point correlation function. Now that alone will give you an n² algorithm, but what my code does to speed this up even further is to give you an n log n algorithm using fast Fourier transforms to calculate specifically those radial coefficients. Those are crucial to constructing the 4-point correlation function. The isotropic orthonormal basis functions are already known. They're easy to pull out or easy to understand. We're not measuring those. We're measuring the radial coefficients. So that's where all the meat of the information comes when you measure the 4-point correlation function with my code. So you might be wondering, what does it spit out? And I'll get to that in just a second. I want to keep you on the edge of your seat, because first we have to discuss what I ran it on in the first place. So this is kind of a heuristic view or not a heuristic view, but a nice plot I made to encapsulate the idea. So we ran the 4-point correlation function looking at all these different tetrahedron-like shapes over what's called a Gaussian random field. And the reason why we chose this is because while it is associated with randomness, you can actually input a known power spectrum into it to create a known analytical model that we can compare our code to. And a Gaussian random field is centered around with a mean of 0. So we're just looking at fluctuations of a field. So knowing what the Gaussian random field is and that we ran our code on it, and knowing that it has predictable results, we ran our 4-point correlation function on this first, and this is what it spits out. So this data set is 6-dimensional, so it's a little difficult to understand. So I'll walk you through the plot a little bit carefully. So we have these L1, L2, L3, and we're looking at these 0th order components to the angles. So L1, L2, L3 are just like basically capturing the angular information of theta 1, theta 2, and theta 3 from this this tetrahedron-like shape. And 0th order is what we're looking at here, aka like the most important order, the highest, or like the lowest order contribution. And so this plot, on the x-axis we have R1, all the different possible bins of R1, and on the y-axis we have R3, and then we're just looking at a slice of R2. So technically this is like a volume cube we're looking at here. And every little square is a different 4-point correlation function coefficient, these radial coefficients that we're talking about. And just like visually what we're looking at, the purple corresponds to a deficit below random, and then the yellow corresponds to an excess of structure above random. And this is looking at correlation throughout the parameter space. So this is really exciting. This is actually what we want. This is kind of what we expect. And when we compare this to other like code and the analytical model, we see like nearly perfect agreement. We ran our code on 10 realizations of a Gaussian random field and took the mean as well as the standard deviation, and that's what this the shaded region is standard deviation. The solid / dashed curves are the mean. On the x-axis, we have a bin index, just looking over all the unique bin combinations. And on the y-axis, we have those radial coefficients multiplied by like a scaling factor of r's. But that's not super important. What is important, though, is just noting this like really great agreement we see between my code, the FFT code, a known trusted code that scales as n squared, which is slower than my code, and an analytical model. So we see this perfect agreement, which is, or not perfect, but it's really close, and this is really exciting. And of course, we looked over many different combinations and scenarios, and we looked everywhere we've looked, it matches greatly. So that's fantastic. So then I just want to get to the results section because this is super important. We ran it on the simulation of the interstellar medium. This is super exciting. You're looking at the first ever measurement of the 4-point correlation function on a simulation of the interstellar medium, which is really exciting. Again, with just the same idea, the black corresponds to deficits below random, and the whitish red, like really bright red, is excess above random. And we, just a little quick note, we did subtract out the mean from this. So we're only looking at fluctuations in the simulation. And that's what we're measuring it on, to be similar to what we were measuring with the Gaussian random field with a mean of 0. So yeah, I can't stress this enough. This is like the first ever measurement of a 4-point correlation function on the turbulent interstellar medium, which is really, really exciting. But yeah, so that's all I have to show today. Thank you. If there's any questions, please let me know.
James, awesome work. Loved seeing that result at the end. That was really cool. Yeah.
Yeah, I had to do a lot of cutting because it was a 10-minute talk last night and I had to get it down to 7 minutes, but I think I whittled it down. I found enough things to remove.
Yeah, mission accomplished. And it's great to see the code working so smoothly. Deshika, you have a question?
No, did I accidentally raise my hand?
You did indeed raise your hand. Adam, do you have a question?
Yeah. All right. So you calculated the 4-point correlation function for the turbulent box. How does it compare to the Gaussian random field? Does it look kind of the same, different? Can you see anything like, can you tell us any story about this yet?
Well, in terms of like comparing directly to a Gaussian random field, just from first eye view, it doesn't look the same. But of course, I mean, I got my code to work literally a week ago, or like less than a week ago. So I'm now just starting to run it on simulations. So future work we're going to be doing is looking at like all the different scenarios from a test bed of simulations on the interstellar medium, looking at factors like how does the like sound speed or the like the alphanic Mach number, for example, affect like what we see with the 4-point correlation function. And it's still running right now for higher orders. So we haven't been able to do like a direct comparison to what a Gaussian random field is. But my short answer is that no, it shouldn't be directly the same. Especially because with a Gaussian random field, we put an input known power spectrum. And in our case, we put a power spectrum kind of from cosmology in there, or not kind of, it is from cosmology that we were able to compare our models to. And so it shouldn't look the same. It would be shocking if they were the same, but the idea of like excess and deficit relative to randomness is what we like are measuring, and that's what we're looking at here. Does that answer your question or no?
Yep.
Awesome.
We'll have to call it there, James. In the interest of time, thank you again for a great talk. Also, go Bears.
Thank you. Go Bears.